Descriptive statistics. The distribution was a little bimodal here. The average is 70, and there's this lovely little gap here. And the average being a 70 was a little throwing based on the fact that the exam average exam one was an 85, almost an 86. Ow. So, two things I need from you. I need you to review this exam carefully. Go through and say, what did I get wrong? What happened? I posted the key to that effect. It's illustrated. I've done things multiple ways using the tables and the calculators and even showing you the Excel commands where necessary. And if it was something that I did not get that was unclear in my explanation to you, I need you to come bug me. If there were specific places where you used, hey, I used the same formula every time and it was always the wrong one, we need to know why that swap happened. And then come talk to me about it, and let's see if we can make this do this so that exam 3 is back up here again. The other thing I need from you is go back and look at the reflection we did after exam 1. These are the things you said you were going to do. Did you? And did they help? And if the answer is yes, great. And if the answer is no, let's figure out what we can do instead. Meanwhile, I want to continue my discussion about confidence intervals based off of Gossett's t-test, the student's t-distribution. And as we said, t-distributions are wider. The tails are fatter than in the normal distribution. So that's always true. And when we have a small number, a low degree of freedom, then the graphs look substantially different, as we see here. But as we gain more and more members of our sample, then our curves get closer and closer together. And as we will see in the table, as our degrees of freedom grow, we approach that normal distribution perfect. So in Appendix D, we have another table. It is a very different table because it only lists what are referred to as critical values. If you're taking calculus, there's this thing called critical numbers. Nothing to do with that. But I'm still trying to figure out how to deal with making my confidence interval, right? So I'm going to have to adjust. And instead of using Z in my confidence interval, I'm going to have to use T in my confidence interval. But again, which T? Please notice, once we get to really large numbers in our samples, this table starts to be inefficient. Instead of going by ones like they do over here, once we get up here, they start to go by 5s and then by 10s. That's not always helpful. So if I'm looking at an oddball number, I'm going to round down in my t-table. I'm going to try and rig it so we don't have to worry about that. But the way around that is to either use Excel or our calculator to do an inverse behavior on a t, just like we had a normal distribution. Oh, I remember where I put my calculator. I have t-distributions right here as well. Numbers 4, 5, and 6 are the t, PDF, CDF, and the inverse, which allows me to get t-values for a given area. In Excel, I think it's going to be on your calculator because you have the different idea about right and left and center. In Excel, we can tell it we want the right tail only, or the left tail only, or the center. The table and the inverse on here works in the center. But notice in our table itself, up here at the top, it says confidence level. And then the next row says for two tail. The one under that says for one tail. If I'm dealing with an 80% confidence interval, well, then 20 should be on the outside, right? But 20 will be equally split between the outside. This is the center idea. If I want one side, I'm going to change it. And it's exactly half. Wait a minute. Go back to what we were doing on Monday. We had that Z alpha over 2 because I was looking at what was on each side. Same idea here. I wrote the formula down and then I moved it. I need the low end and then I need the high end. So let's go back to Monday's formula. Monday's formula said we took the average. We then either added or subtracted Z alpha over 2 times something. What was the something? That's this number, right? That's the Z alpha over 2. What was multiplied by that? Emma?
Standard deviation over the square root of n.
But that was where we knew the standard deviation, right? We wrote sigma. But remember, I said up here, we're doing a confidence interval for a mean with an unknown standard deviation. The T takes into account the fact that I don't know the population standard deviation and allows me to use the standard deviation from my sample. So instead of sigma over the square root of n, I'm going to use S over the square root of n. So it's still the same idea, standard deviation over the square root of n. But this time, both pieces, X bar and the standard deviation, are from the sample, mean and standard deviation. Both come from my sample. So this is an estimate of the standard error rather than the actual standard error. And that's why we use T instead of Z. So, an example. Problem number 21 down here. A random sample of 10 items. Crap. What happened? I lost my camera again. Turn back on. There we go. A random sample of 10 items is drawn from a population whose standard deviation is unknown. There's the piece that tells me right there. I'm going to use a T instead of a Z. The sample mean is 270. Sample standard deviation is 20. Okay. Let me write down the pieces of information we were given in this problem. Problem number 21. A sample of 10 items is taken from a population whose population standard deviation is unknown, but the average is 270 from the sample, and the standard deviation from the sample is 20. Use the table to look up the t-value. If you've got your textbook, Appendix D is where we're at. If you don't have your textbook, feel free to open the Canvas page where all of the tables are in that zip file at the top of the section labeled Doan. That's the author's name, which is why I said it that way. We want an interval estimate with a 95% confidence. 95% CI for the mean. I want you to give me a range where I can say I'm 95% certain the correct average is between these two numbers. So, first thing I need to do is I go to my table and I say to myself, I want a 90% confidence level. Oh, sorry, 95% confidence level. 95% confidence levels are right here. So that's the column I want. And I want degrees of freedom. I have 10 items. What's my degrees of freedom? Okay, that's the problem. 2.228 goes with degrees of freedom being 10, right? But according to what I said on Monday, my degrees of freedom takes one away from that number. So instead of using this row, I want to go up one more and use 9. So even though they told me how many people I have or how many things I have, the degrees of freedom, n minus 1, so that's 10 minus 1, that's 9. And then the t-value, it should be t of 0.25 because it's alpha over 2, right? 95% confidence interval means the alpha is 0.5. Half of that is 0.25. And what number did we come up with? 2.262 out of my table. Now notice, if I go to the calculator, I know the area of the piece I want. The area of the piece I want is this big. I'm going to use both a positive and negative version of this, right? So I could get the t-value that's the cutoff on the left and it would be negative. I get the t-value that's the cutoff on the right and it would be positive. To get the t-value I want, I know the area, I'm using the inverse. Distributions. Number 4 says inverse t. Hey, tell me the area you want. I want the area to be 0.025. I have 9 degrees of freedom. And notice that's the left number because it gave me the negative one. The area was just this little piece. If I want the positive one, what's the area I want? I want all of this area.
Positive 2.26.
It'll be the same number. But what number would I put here to get it?
75.
Say again?
75. 0.0.
975. Because I need to get to 1, right? As a matter of fact, if I change that to read 975, then I get the positive of the same value. So that's my t-value. And if I don't want to use the formula sheet, I use this. I can do it in Excel the same way. There's a t dot inverse, like there's a t distribution. But now I have everything I need to do my confidence interval. To do my confidence interval, I take the average minus this t-value times standard deviation over square root of n. Somebody give me some numbers.
But 0.694.
I'll call there. That's one.
283.
Great. So now I can say I am 95% certain that if I went and surveyed the entire population instead of just a sample of 10, that the actual average would be between these numbers. Since my sample gave me a 270, 95% certain this is the right range for the overall behavior. What do you think's going to happen if I survey more people? What if I did 20 people or 40 people? Is the range going to get larger? Why is it going to get larger?
Because with more people, there would be more of a range between all of them.
But if my sample still gave me the same average and the same standard deviation, then it should get smaller because this number will go up, right? But more than that, this number will also change because my degrees of freedom will change. And when I go back and look, if I went from 10 people to 20 people, instead of DF being 9, it would now be 19. And notice that that number is smaller. It's 2.093 instead of 2.262. Because as my numbers go up, the tails get smaller and we look more like a normal distribution. So the top number here doesn't change, but the bottom got bigger and this number got smaller. That means the overall fraction got smaller. The more people we survey, the narrower, the more confident I should be that I got the right number. On our Canvas page, there are a list of sample problems. Both 25 and 27 on page 291 are given data files. So 25 gives me rents paid by 12 people living off campus. And then I want to know what's the average rent. And then 27 says I'm looking at exam scores for 3 different courses. For 3 different exams in the same course. And I want to know what the confidence intervals are there. But with small numbers, I don't want to use Z. With an unknown standard deviation, I don't want to use Z. I did them in Excel. You can find them on our Canvas page with the Excel files. So you can see how all of those same numbers are generated with Excel commands. Questions? That's just what the number is at the edge of the interval. So for the t distribution, which is going to look like a fat tail version of our normal, right? When I cut it off and this area is 2.5%, the cutoff is 2.262 with DF being 9. So that's the edge. And then the negative one would be down here. There'd be 2.5% here. And that means that the middle is 95%, which is why I can call that my confidence interval. But those are what the text table is labeling critical values. They're the values where I make the cut based on my confidence interval, rather than give you all the possible cuts for all the different z values. Because there are so many more different curves because of the degrees of freedom changing, I need a new table for each degree of freedom. Well, that's a pain in the ass. And since I really only ever use 90%, 95%, 99%, sometimes I use 98%, sometimes I use 90%. That's why there are 5 columns in this table, because those are the most commonly used values. I don't even look the rest of them up. If I really do, I've got the ability to do so with technology, rather than doing all the calculus required. So, if I have a mean, and I'm looking for a confidence interval around that mean, I need to know whether or not I know the population standard deviation or I don't. Z when I know it, T when I don't. But that was not my only minimum variance unbiased estimator. The mean was a X bar was a good estimator for mu. And this is how good it is. How big's the variability? I said that proportion also had a good estimator in P. Now, the proportion that comes out of my population was pi, and its estimator was P. Proportions are always between 0 and 1. You're looking at a fraction of the population. You can't tell me that this following thing is true for 130% of the people. Doesn't make sense. But I can think of how many times did the thing I want to have happen out of how many times I did the survey or experiment or process. This is my sample. This is the number of things that went the way I wanted. I make a proportion. Take the fraction. Now, the other way to think of this is that this is an average, but it's an average of data that are either 0 or 1. It didn't happen or it did. And if I average all of those, well, that's going to give me some fraction. This is a consistent estimator, which means I should be able to use a normal distribution, provided I have enough people. But if this is a proportion, I need to think about how I get my standard deviation. But we had a number for that. We had a way of figuring out the standard deviation. It should have been on your formula sheets. Because this is either 0 or 1. I think of this as some sort of distribution. There was something with a square root for a standard deviation. And I think we had P times 1 minus P. But now I'm looking at the population, right? So wait, I don't want to use P. I want to use pi. 1 minus pi. But that's my standard deviation. And if this is population, that won't be S, That'll be sigma, won't it? That's for the population. I can use a known population, a known standard population standard deviation. Aha! Therefore, my standard error looks like dividing by n, the size of my population. Now, when we did the standard error for the mean, we called it sigma with a little x bar on it, right? Now I'm calling it sigma p because we're dealing with a proportion. Again, the more numbers, the larger a sample size, the closer this is going to look to a normal distribution. Page 292, figure 18. Which means if I'm really using a normal distribution, I can use z-values. As long as n is big enough. Now, what's sufficiently large in this case? Well, how large? That really depends on what I know about pi. What's pi? Pi is our population proportion. When we did the drug testing thing back when we were doing Bayes' theorem about reversing conditional probabilities, I said we made an assumption that 4% of the population used drugs. That's 4% of the population. That's our pi, 0.04. And that's the issue. If I know that, then I should be taking a really large sample. And there's this lovely table here on page 294 that says what we really want to get is we want to get at least 10 yeses and at least 10 nos. And if x is the number of yeses, then n minus x is the number of nos. So if I have a 50-50 chance, then I would expect to get 10 yeses and 10 nos in 20 people, right? On page 294, there's a list. If my proportion is 50%, 0.5, then it should only take me 20 people to get 10 yeses and 10 nos. But if it's 40% or 60%, because if yes is 60%, then no is 40%, and vice versa, right? Then it should take 25 people. For me to get 10 yeses and 40%, well, then I need half again that many to get the 60%. and so on. I can work my way through. Notice that by the time I say I've got a 0.05, then I need 20 times to get 10 yeses. I need 190 no's, which gives me a 200 people total. If I said that the drug population, the percentage of people using drugs is 0.04, I'm going to be between 200 and 500 people for my sample. So I really can't do that with a small group. I can only use Z when I have large numbers like this. So when we talk about drug testing, we're looking at national numbers to get that 4%. I'm not looking at Seton Hill people. I'm not looking just on campus. I got to look at the nationwide averages. Otherwise, I don't have anywhere near enough people. If your sample is too small, then I'd need to try and do a binomial estimate instead of a normal. And that's just really complicated. And I'm not going to do that. There is a nice, easy way to do binomial estimation in Excel, Ministat, StatLab, R, Orange. Lots of data analysis will do that. We rarely run into those encounters in the real world, unless you're doing really narrow surveys. Like, let's talk about drug use on the Seton Hill campus. We're not going to get anything that ever surveys that because we don't want to know. But now I know the standard error. And I can estimate it with the standard error of P rather than pi. And that means I can use my normal distribution. So to do a confidence interval for pi, I'll start with P and I'll subtract Z alpha over 2, and then I'll put my standard error. And then I'll do the same thing, but add. Again, because I'm saying, oh, larger samples give me what is effectively normal, I can use Z. If we want to narrow the confidence interval, I then change alpha. Say, all right, well, I'll allow myself a little less confidence area, or increase my sample size. But that's horrible. The most recent set of examples I can think of this are the presidential election that just happened. How many surveys did you see that before the presidential election? We think this much percentage of the people are going to vote for Biden or Harris, depending on when it was. We think this percentage is going to vote for Trump, right? You saw that in every city. We saw it nationwide polling. They did all this. They called thousands of people every freaking weekend to figure this out, right? And then they gave a margin of error. Margin of error. So if I say, I'm not going to ask you who you voted for, but if I say, you're a voter, I got your vote, I put you in the list, but I don't know who you're going to vote for, and I have no way of knowing who you vote for, I just called you up. So I'm going to assume there's a 50-50 chance you'll vote for Trump or Harris. That's 50-50. That's assuming my pi isn't. That's assuming the population proportion. Oh, so if I assume that that's 50-50, then this no longer depends on what P is. That's assumed. Almost all of the confidence intervals given in voting use a 95% CI. Okay, I'm back on the normal distribution, Appendix C. 95% means I need Z of 0.025. So I need to know what Z value goes in an area of 0.025. That's the one in the box, 1.96. Well then, what's this number? If I use 1.96 for the Z and I use 50% for P, then this piece is my margin of error. That's how much to either side I would be. Oh, the margin of error would be 1.96 square root of what? Well, I'm going to assume this is 50%. What's this one? It's also 50%. Well, that just made my life really easy, didn't it? So the top of that is 0.5 times 0.5. That's squared, isn't it? And when you square root a square, they cancel each other out. So I have 1.96 times a half over the square root of n. The more people I survey, the smaller my margin of error gets. By the way, in presidential politics, the margin of error that the major surveyors have used for the past 50 years has been 3%. If I want a margin of error of 3%, do you know how many people I need to find? I don't know off the top of my head, but I can figure it out, right? If I want the margin of error to be 0.03, you can figure out what n is. 0.03 equals 1.96 times 0.5 over square root of n. So I'm going to multiply the square root of n over to here. 1.96 times 0.5, and then I'm going to divide by the 0.03. Give me a number. That's this number, right? 32 point something. But that's the square root. So to get n, I need to square this thing, right? Go ahead, Em. To have a 3% margin of error, I need to poll less than 1,100 people. Every survey you see on voting has spoken to less than 1,100 people. They're trying to predict the behavior of 240 million voters, and they're asking 1,100 people. Ask more, damn it. Why don't they? I don't have enough time. And I'm going to have to spend a whole lot more time calling people, aren't I? And that's going to cost me in the hours I keep people in the phone banks making all these phone calls. Plus, they get hung up on all the damn time, right? I'm from so-and-so presidential polling. Click. Damn it. And so the trade-off was made to decide that that would be an acceptable margin of error. There are lots of other potential sources of error. Bias, right? In this case, opt in. The people who want to tell you about the vote really want to vote, regardless of which way it is. They really want to vote. The great pile in the middle who are like, whatever. That's the problem. That's the undecided voter. And that's why they focus on that so much. Overcorrection for trying to figure out the diversity of the population. If I'm looking at Westmoreland County leans red. So if I need to make sure I ask enough Democrats and enough Republicans, ask enough white people, black people, male people, female people, people who own, people who rent, people who are wealthy, people who aren't, I'm going to spend a lot of time making more and more phone calls trying to make sure I get a good snapshot of what the average Westmoreland County feels like. Population density. I think I've given this story before. Harry S. Truman is shown being the day after the election holding up a paper that says Dewey beats Truman. Do you know why the newspaper ran with that headline? Because Dewey was the Republican candidate and they called people to do a survey. Truman is 1940s. Only rich people had phones. And all those rich fat cat Republicans, they were going to vote for Dewey. If I miss the population, then I misrepresent my error. Questions? Again, I've posted a number of examples to our Canvas page.
This for statistics, do you have to go into psychology at all? Because of like, if you announce on the news that somebody's in the winning spot, a lot of people want to be in the winning team, quote unquote. You keep saying this person's going to win, this person's going to win. People might switch over to that person.
Oh, yes.
Hear that that's the winning team.
And sometimes the reverse happens. People hear so-and-so is going to win, so-and-so is going to win, and it motivates the opposition. Well, get the hell out there and do something about this. They haven't won yet. There is enough psychology in both directions that if I just say, this is what the numbers predict, I can be accused of bias by either side. I'm talking this person up. You're talking this person down. I'm just talking. The numbers show me this. You make with that what you will. Nobody believes that anymore. To that end, that's what's done predominantly in commentary. News shouldn't do that. News should just say, here's what our survey said. Commentators will then go, okay, now we want to motivate voters here or here or what. Take this same idea, move away from voting. Hell with voting. Anybody remember the Cola Wars? This is from my childhood. Coke versus Pepsi. Michael Jackson lighting his hair on fire. You all need to look this stuff up. Michael Jackson did a Pepsi commercial. Pyro lit his head on fire. Not a fun picture. Coke versus Pepsi. I don't care what you drink. But for years, they were fighting each other to be the top soda in the country. And they started doing blind taste tests. Pepsi put out a commercial where they covered them up. There were two straws sticking out of the box. Which one do you like better? 75% of the people in that blind test voted for Pepsi. Do you know what Coke did as a result? They changed the formula of the drink. New Coke. And that's why what you drink today is called Coca-Cola Classic, because that sucker flopped hard and lost the company $1 billion. Doesn't have to be politics. There's a lot of money to be made understanding how big my survey needs to be. For the record, I think they only surveyed about 85 people in the blind taste tests. They kept trying to do bigger ones, but they didn't often. Other questions? Need to look something up. Yes. Okay. One of the things that happens sometimes is you do a bunch of surveys or samples or trials like we did with our Bernoulli idea, and you actually get a p-value of 0. You get the thing you were looking for never happened. Well, then I need a confidence interval. How sure am I that it should never happen? Come on, even a rare event happens occasionally, right? If I've got n trials, then a good upper bound for that 95% confidence interval is 3 over n. Why 3 over n? Remember our normal distribution? And we said we could go down 3 standard deviations or up 3 standard deviations, and we'd get 99.7% of it. So it's really unlikely to be outside 3. I'll use that as my confidence interval. 3, 1 over n, like a uniform behavior for each trial. This really comes from trying to approximate our normal distribution, using either a binomial or one of the other distributions that we had. This is useful in the case of limited data. If I'm trying to test bumpers for failure, I don't want to wreck a whole dozen 200, 300 cars, right? For something that's going to be rare, I want to do that as few times as I can. And so in cases of limited data, having something like this is fairly worthwhile. I deliberately didn't do a lot of examples today. They are posted. Please read through them carefully. This is leading me to how to answer questions. Is the following thing really reflective of the overall population? I got 2 more things I want to talk about confidence intervals. Then we'll be done with this chapter. That's what we'll do on Monday. I hope you have a wonderful weekend, and we'll see you all then.